Okay, good morning. Hope your day is going well. Thank you for being here on this lovely day. So thanks for being inside with me. Anyway, today we're going to do review for the upcoming midterm. And that's kind of what I'm trying to gear us all up here ready for. When you come to class next Monday afternoon, all right, you'll turn in the acid and base titrations lab, which we did on Monday. Exam prep 1 is up, and exam prep 1 is a single page, double-sided with some questions followed by the answer. And I want you to show your work how you go from the question to the answer. And I'm really hoping that these aren't like super hard, but that being said, you get to question number 3 and you're like, whoa, reach out to me, all right? Or reach out to the Learning Success Center, stuff like that. I want you to have these skills before you take the midterm. And then the midterm will definitely be up. We won't do problem set 4 or quiz 4. We'll take the midterm instead. And the midterm is basically over problem sets 1, 2, and 3, which is more or less chapters 13 and 14. There's a little bit in chapter 15 with Lewis acids and bases, but most of it is 13 and 14. So we'll do things on equilibrium. We'll do things on Le Chatelier's principle. We'll talk about acids and bases separately, how to calculate the pH, and then we'll go into things about buffers and how to do acids and bases together, like in a titration. So those are kind of the things. Now, the midterm itself will have 20 multiple choice questions, 4 short answer questions. It'll be about 2 hours in length. You will have access to the titration calculation sheet that you used on quiz 3. The very last page of the midterm, I'll talk to you about this next week, but I want you to just rip it off and you can have it right next to you. This will be the sheet from quiz 3, and you can still bring in your own note sheet too, by the way. Anything handwritten, front and back, 8.5 by 11 piece of paper is fantastic. Of course, you'll have your calculator. We've got periodic tables for you. And then the next time I see you, I will return the midterm. It'll have a summary sheet at the end saying like how you're doing in the class as of this moment, stuff like that. There is a sample midterm. I think I said it, but I'll say it again, online. So you can look at a midterm from a few years ago to kind of see what's happening, what my formats are, things I'm looking for. Any questions on anything? All right, so what we're going to do today is go through a series of test questions, all right? And these are things I consider to be test worthy. And I encourage you to try the problems on your own. I'll give you a few moments to kind of work on it. After a while, we'll talk about the right answer, all right? So it's okay if you make mistakes, all right? And actually, I would encourage you just to try, because I want you to get all the mistakes out now so that when you get to the midterm, you'll be able to rock and roll and take care of business. So without further ado, let's check them out. Anybody have any questions? Sweet. So this is an equilibrium question, all right, where we're trying to find the equilibrium constant Kc. And what we're doing here is we're placing 0.010 moles of dinitrogen tetroxide in a 2-liter flask. And once it achieves equilibrium, the dinitrogen tetroxide is now 0.0038. And you can use this information to calculate Kc. I would set up an ice table to do this kind of problem. You can figure out how much the N2O4 has changed, and then apply that to the NO2 to calculate your K value. So see if you can check this out. I'll talk about it in a few minutes here. Okay, so on a question like this, ICE table would be really, really helpful. And again, ICE is an acronym for initial, change, and equilibrium. And what I usually do is I kind of write the equation up here, all the things that are, anyway, that are either gaseous or AQ. Don't put solids and liquids in there. Another thing about ICE tables is that you should really, really, really use moles per liter. Once in a while, you can squeeze by with moles, but on this one, it makes a lot of sense to keep it in moles per liter. So you can see here you have so many moles in a 2-liter flask. So 0.010 divided by 2 will give you the molarity, and that comes out to be 0.0050 molar. So that's the initial concentration of N2O4. Now, in a problem like this, you don't have any NO2 to begin with, so that's 0. So to fill out the rest of it, you can also see here that at equilibrium, the N2O4 is 0.0038. So I put that down here in the E line. Now, the change part is often the key to figuring out these K values, all right? Because the change has 2 things that are important. First of all, there's always a line between reactants and products. And it's an important line because one side of that line, all the numbers on the change line will be negative, and on the other side, they'll all be positive. Now, most of the time, the reactant side is negative and the product side is positive, but it is possible to have a reverse, so just FYI. The other thing is that the stoichiometry of this reaction, which just means 1 N2O4 for every 2 NO2s, this 1 to 2 ratio is going to be very obvious in the change line, all right? And finally, you can't have any negative numbers in the E line. K values are always positive. So that's why answer E here doesn't make any sense at all. Negative numbers and even 0 is not acceptable for equilibrium constants. All right. So to figure out the change part for N2O4, it's literally the top number minus the bottom number, the 0.005 minus 0.0038, because that's the amount that the N2O4 changed going from the initial amount to the final equilibrium part. So the N2O4 went down by 0.0012 moles per liter. And as much as this went down, we can make some kind of connection for how much the NO2 went up. So this one's going to be positive here because as this was used up, we made more NO2. But it's not as simple as 1-to-1 because one N2O4 makes two NO2s. So if we used up 0.0012, that means we're going to have twice that amount of NO2 being made. So I multiplied the positive version of this by 2 to figure out that there's 2 NO2s for every N2O4. So at equilibrium, we've got 0.0024 for the NO2 and 0.0038 for the N2O4. Any questions on that part so far? Cool. All right, equilibrium constants, always products divided by reactants. If something has a non-zero, non-one stoichiometry, raise it to that power. So NO2 is, squared, and 2O4 is just to the single value. So what I would do here is take 0.0024 squared and divide it by 0.0038. And if you do this, you get 1.5 times 10 to the minus 3 answer. Okay. Cool. Any questions on that? One thing that kind of helps a little bit is that K is less than 1, and that means reactant favored. And at the end, you'll almost always have a bigger number for reactants than you will for products. Now, there are some weird math things that happen once in a while, but more often or not, this is the case. So notice that 0.0038 is bigger than 0.0024. This is another way of saying you've got a reactant favored condition, like you've got more reactant at equilibrium than you have product. So, question? All right. So here's a reaction where we have two types of equilibrium constants. The first one is nickel-2 carbonate becoming the ions, and the second one is actually a Ka expression, although you don't need to know that, for hydrogen carbonate making hydronium and carbonate. But in this problem, we want this reaction. All right, we want to know the equilibrium constant for this one. So what I'd like you to do is try to combine these two equations to get the K for this equilibrium constant. So you want to combine these two equations around and end up with this stuff right here. And you can probably see, for example, carbonate is a product in both of these reactions, and there's no carbonate here. So somehow, some way, you're going to flip one of the reactions around and get rid of that carbonate because we don't want any carbonate here. So see if you can figure this out. We'll talk about it here in a little bit and stuff. So. Okay, so when I have a problem like this, I want to see how we can combine these two equations into this down here. And like I told you, carbonate appears as a product in both of these reactions, and there's no carbonate in the desired reaction. So what that means is we're going to have to flip one of them around, all right? And the goal is to figure out here which one we're going to flip. So if you look here, like nickel 2 carbonate is a reactant in the desired equation. So NiCO3 is a reactant in both, and likewise nickel 2 plus is a product in both the first equation and the desired equation. So what that means is we don't want to flip that equation around. All right, we want NiCO3 as a reactant, and we want nickel 2 as a product. But if you look at the next one, hydrogen carbonate is a product, and in K2 there, it's a reactant, all right? So that is strong evidence here that we're going to flip it. And if you keep going, you can see water as a reactant ends up as a product, and hydronium, which is a product, ends up as a reactant. So what this tells you is that we want to flip that K2 reaction around. And what I often do is I just literally rewrite it just to make sure that everything's good to go. So we have carbonate and hydronium in equilibrium with hydrogen carbonate and water. And you can cross out or just do this one. And why I find this useful is that if you combine then this equation with this equation, you should end up with this down here. So for example, nickel 2 carbonate comes down and hydronium comes down. So that's good. The carbonate, which is a reactant here, will cancel the carbonate, which is a product there. So carbonate will be like on both sides of the reaction. It essentially cancels out. But we still have the nickel 2 plus, we've got hydrogen carbonate, and we've got water. Cool. So that's the first step, figuring out what you're going to do. We're going to flip that second equation around. Questions on that? Okay. Now, what do you do to K if you flip the reaction around? What was product favored becomes reactant favored, etc.
Take the reciprocal.
Exactly, you bet. Take the reciprocal. So K2 is just a number, all right? What we're going to do here in a little bit is go 1 over K2. We're going to take the inverse of it, the reciprocal, like Kevin said. And that's important. We're not going to do anything to K1, so that'll be good. So when you combine equations, the net K is just the K of the first one times whatever the K of the second one is. So what we're doing here is we're going to take K1 and we're going to multiply it by the reciprocal of K2. So it'll be 6.6 times 10 to the minus 9 times 1 over 4.8 times 10 to the minus 11th. Or you could just go 6.6 10 to the minus 9 divided by 4.8 times 10 to the minus 11th. But either way, if you do all that, it comes out to be 140, all right? And so this is a product-favored reaction, Gesundheit. And this might be one of the things that a chemist wants to know. And what this is saying is that the insoluble carbonates react with acid to make a bunch of dissolved stuff. And that's true. That's actually something that happens. This number kind of confirms it. It says, oh yeah, it's going to be product favored. You're going to be good to go. But I'm more interested in the fact that you know how to combine equations. You flip it, you take the reciprocal, add them together, means multiply the K's. Any questions? Now, this next one, I'm not going to open up for the iClicker thing because this is one of the most complicated questions in all of Chem 223. So I just want to go through it and tell you how you would solve it because I think there's some value in that. So first of all, in this problem, hydrogen and iodine are reacting to make hydrogen monoiodide. and the equilibrium constant is 54.3. And we have initially concentrations of H2, I2, and HI, and the question is find the equilibrium concentrations once everything is settled. And there's all these 5 different values. Now, why this is a little wild, all right, is first of all, we don't know if reactants, these two, are going to go to products, the HI, or if HI, the product, is actually going to backpedal and go back to reactants. We don't know the direction, so when you get to the change level of the ice table, we don't know where the positives and negatives are. So the first thing in this problem that we would have to do is we would do Q versus K. We would use these values up here to find Q, compare it to K, and that would tell us the direction, i.e. are H2 and I2 going down and HI going up, or is HI going down and H2 and I2 going up? And once we have that, we would then use the ice table to solve for the equilibrium concentrations and stuff like that. So again, I just kind of watch me here. This would not be a question I would ask, but I think there's some value in seeing it. Q is really helpful. If you have a question like this and you don't know which one's going up, because reactants, are they going to go down or products going up? That's where Q comes in really handy. So in this problem, to solve it, what I would do is first solve for Q. And Q looks just like K. All right, it's HI squared over H2 and I2, just like K would be. But the difference is we're using all of these values right here. Now remembering that K is 54.3, this Q comes out to be 69.7. Now, if we would have had K and Q be the same, score, it's at equilibrium. We're good, we're done. But darn it, Q and K are not the same. So if Q and K are not the same, there's 2 conditions. Now, most of the time, honestly, Q is less than K, so that means reactants will turn into products. So the reactants would go down and the products would go up. But lo and behold, in this case, Q is greater than K. So probably how this happened is someone started with HI and they're just watching it decompose into H2 and I2. So what this number means when Q is greater than K, that means your products are going to go down, the product amount that you have, this number, and the reactant values are actually going to go up. So that's one reason why this problem is just a lot of fun. Next thing you would do is you'd set up the ice table, all right, reactants, products, ice. But here's the part where Q helps out, because normally reactants are negative and products are positive, like on the NO2, N2O4 thing we saw earlier. But because of this Q thing, it's actually flipped around. So you've got these wild values. You'll place it into the expression for K. You end up with a quadratic formula. Throw it, I used my solve button on this one, just to let you know. So anyway, there's a positive number and a negative number. Negative numbers are never allowed. So this positive number is what we want for X when we plug it back up here. And just as a quick reminder, if you have a quadratic, if there's positive and a negative, you always want the positive, because negative mass, grams, moles per liter doesn't fly in chemistry. So the positive number is what you want. If you have 2 positive numbers, you want the smaller one, because almost always the larger one, when you plug it back in here to one of these things, will give you a negative mass. So if you have 2 positive roots, you want the smaller one. If you have a positive and a negative root, you want that positive one. In this problem, we're going to take the positive X and run with it. When you do all that, you get all these values here for H2 and I2 and HI, which was answer D. Voila, all right? But there's another reason why I wanted to ask this question, all right? Because one other thing you could do is you could go through all the possible answers and see which one came up to 54.3. So let me show you these numbers again. Here's all these numbers, and you saw all the work that had to be done to it. If you put HI squared over H2 and I2 and you get 54.3, you're probably good, all right? But if you got like 100 or 0.01, then you won't get the right KI. So instead of doing all this Q and K and figuring out quadratic formulas and having a fun time, sometimes if you just put in the values, you can find K2. So, all my secrets are yours, I promise. And this is one I've used once in a while when I didn't feel like doing Q and K and quadratics and blah, blah, blah. Anyway, just to let you know. Any questions on this? Okay, let's go back to some stuff that we can do. This is a question where we have a delta H, which is negative. Negative delta H, does that mean exothermic or endothermic? Exothermic, yeah. Exothermic and negative delta H go together, all right? And why that's important, that means that heat is going to be a product. And for Le Chatelier's principle, when it comes to temperature questions, you have to know if heat's going to be a product or a reactant. So negative delta H means exothermic, and exothermic means heat's going to be a product. If this would have been a positive delta H, that would have been endothermic, and heat would have been a reactant. So knowing that this is exothermic, we're going to all of a sudden cool this reaction down. What's going to happen to K? All right? See if you can figure out how this will affect K. We'll talk about it here in a little bit. Okay, so this is a Le Chatelier's principle question. And Le Chatelier's principle, in a nutshell, if you add something, it goes to the other side. So let's look at this top reaction. Let's say I add chemical B, all right? The reaction's gonna move to the opposite side to make more A, all right? This also applies to heat, we'll talk about in a little bit. Now the other thing you can do is if you take away a chemical, so we're gonna take some of the B out of this equilibrium, the reaction tries to make more of what you're taking away. So if you take away B, the reaction will shift to the right, to the product side. If you add B, the reaction will shift to the opposite side of what you add, so it would add to the left. So you add A, moves to the right, take away A, moves to the left, etc., etc. This also applies to heat, and this is why it's really important to know if it's exo or endothermic. Now, exothermic means heat is a product, heat's being generated. So this is the one we're going to look at here. Now, all of a sudden in this reaction, we're suddenly taking away, we're lowering the temperature, all right? And that's like making the reaction cold, all right? And if you get cold, you probably put a coat on or a sweater or something like that. That's also what reactions do, but they don't have sweaters and coats, but they can make more heat if they, depending on what the value of this is. So this is exothermic, heat's a product. Making it go cold is like taking away heat. So that means this reaction is going to shift to the right. And if you have a shift to the right, your K will get bigger. So we would expect the value of the equilibrium constant to get bigger here. Now, if this would have been endothermic and heat was over here, it would have been the opposite. It would have decreased. And again, that's why it's really, really, really important to know when you have something exo or something endothermic. Any questions? Cool. Now, with temperature, you actually change K, all right? So that's why in this case, K actually does get bigger as you lower the temperature. The endothermic reactions would be the opposite, and we'll talk about this more coming up here. Cool. So in this case, by the way, K would go from 10.5 maybe to like 50, 100, I don't know, it depends on what the temperature change is, but there would be an actual, the actual value of K would get bigger. That's the idea here. So. Okay, so here's a question now where we're going to shift gears. We're going to start talking a little bit about acid and base. And we're putting in this reaction 0.535 grams of sodium hydroxide in 100 milliliters of water, and we want to find the hydronium concentration. Now, one hint that I want you to think about is, does hydroxide give hydronium explicitly? And I want you to think about that as you answer this question. So see what you can do here, and we'll talk about it in a little bit. So on this problem, you're starting with sodium hydroxide, and this is the molar mass of sodium hydroxide, and it asks for the hydronium. But the weird thing here is that hydronium is the hallmark of an acid, and hopefully you're starting to remember now that sodium hydroxide is one of the strong bases. So we have to translate what is a basic value into an acid value. Grams of sodium hydroxide divided by 40 will give you the moles, and moles divided by the volume in liters will give you the molarity of the sodium hydroxide. And for every mole of NaOH that you have, it's going to break down to Na+, which is pretty boring chemically, but you're also going to have hydroxide. So that's the first thing you want to do. You want grams divided by 40 divided by 0.1. That's going to get you the moles per liter of the hydroxide. And I think it's this number right here, 0.134 moles per liter. But this isn't the answer. This is the hydroxide, and it's a pretty big amount because sodium hydroxide is a base. It gives hydroxide. So to finish this one off, water auto-ionizes into hydronium and hydroxide. And this was what the whole purpose of the Kw expression is. And so for this reaction, if you wanted an equilibrium constant, only put aqueous and gases, don't put liquids and solids. So the K, which is Kw, would be hydronium times hydroxide, and you just divide by 1. And this is the only K that I want you to know. It's essentially 1 times 10 to the minus 14th. So if you take this K, Kw, and you divide it by the hydroxide concentration, it comes out to be 7.48 times 10 to the minus 14th moles per liter, which is incredibly small. There's not a lot of acid when you have a lot of base. That's kind of the idea here. But this is how you can convert. There's actually a little tiny bit of acid and base at the same time, hydronium and hydroxide. But when you have so much hydroxide, you're going to have very, very, very small amounts of acid running around at the same time. Any questions on that? Cool. So make sure you know Kw, all right? Kw once in a while will pop in. It's just 10 to the minus 14th or 1.00 times 10 to the minus 14th. But it is a number that pops in. And every time we use 14, like pH plus POH equals 14, that stems from Kw. So it's pretty important. Okay. Here's a question. It's kind of like the first one we did, or the second one, I guess. We have H2S and HCN, which both have a Ka. And the question is, what's the K value for this reaction right here? So again, what you're going to do on this one is you're going to write the Ka expressions for both of these. You'll probably end up flipping one of them around to get this expression, and you can combine the Ks. Now, a hint, Ka is always acid plus water, and the products are hydronium plus conjugate base. So for this one right here, you'd have H2S plus water, and hydronium and SHS minus would be your products. So see if you can do all this, combine them, find the K, and then use the K to figure out which one of these it is. See what you can do with this, and we'll talk about it here in just a little bit. Okay. On this problem, how I would solve it is kind of what I did up here, which is like what we did earlier. You write the two equations out, you see how they mix. So HCN is a reactant in this one, and we want HCN in the desired equation. But H2S is a product, and in this Ka expression, H2S is a reactant. So we'd end up flipping the Ka for H2S around. You could then combine the Ks, which is 4 times 10 minus 10th, but we'll take the reciprocal of this K because we need to flip it around. So it's like 4 times 10 to the minus 10th divided by 1 to 10 to the minus 7th. It comes out to be 4 times 10 to the minus 3. That's a reactant favored K. So we would say equilibrium lies to the left. However, if you don't like my math way, there is another way to do this, because the stronger Ka always pushes to the weaker Ka. And in this problem, this is a bigger Ka than this one is right here. And H2S is a product, while HCN is a reactant. So another way to do this without doing math is bigger Ka pushes to the weaker Ka. And if you do that, this is a bigger Ka. It's going to push to the weaker Ka, which is HCN. That's another way to see that this is going to go to the left. So either hand waving using Kas, or you can actually calculate K like I did up here on the board. Either way is awesome, but it's going to be reactant favored. Equilibrium will shift to the left. Cool. So more than one way to win. Oh boy. Questions on that? Okay, we will do more of this on Friday. We'll start off with this one with the HCN kind of stuff. Thank you for being here. See you on Friday. Have a great day.